Okay, so here we go. And use the blue. So today we're going to be continuing our look at limits. All right, we're going to dive into the idea of continuity too. We've been mentioning the word continuous, right? I've been mentioning the word continuous, I guess. But now we're going to actually dive into it and kind of examine what, kind of a more formal mathematical definition. You've probably been talking about continuity since, I don't know, maybe middle school or something like that. Just having nice, smooth functions. But now we're going to use limits to help us, formally define what it means for a function to be continuous at a particular point. Okay, so we'll just kind of look through here. So continuous, right? A function is continuous at x equals c, so at a point c, if there is no interruption in the graph of f at c, right? That's kind of the idea that you guys have had in your head, or developed at least in your head maybe since, middle school, whenever you started thinking about this idea. So, no holes, no jump discontinuities, if you, think about, absolute values, some of the absolute value stuff where we was, so we know what holes look like, but jump discontinuities can look like, something like this. Okay, that would be a jump discontinuity there. Or, of course, infinite discontinuities. Those are your asymptotes and things like that, too. Okay? So, first thing we're going to look at here, okay, the actual definition. You'll notice there are 1, 2, 3 kind of requirements that must be met for us to, officially say that a function is continuous at a particular point. And there's that IFF. Remember, that stands for if and only if. So you can only say a function is continuous at a point C if these 3 things are true. Okay? So let's take a look here. So first of all, the idea we want to say f of c must be defined. Must be defined. So an example. Okay, I'm just going to draw a picture here. F of 0 is defined. Okay, so there's a picture. F of 0 is defined. But notice, again, is this enough? Is this enough to say that this function is continuous? Clearly not, right? This function is not continuous. We got to jump here. Okay? So that one characteristic, that one property, if it's true, if it's there, okay, that doesn't guarantee we're continuous because, again, f of 0 is defined. Now, granted, all the other function values are defined, and we are continuous along here. We're continuous along this interval, but then if you consider the whole function together, there is one discontinuity at 0. But we have met one of our requirements. F of 0 is defined. Okay, so there's that. But the limit as x approaches 0 of f of x does not exist, right? The limit there does not exist, okay? And that's a key thing because we go to number 2, and we're required that not only must the function be defined at c, f of c must exist and be defined, but the limit as x approaches c of our function must also exist, okay? Must also exist. So just as a picture of that. Okay, so there's a different function, and I'll say that's so here, the limit as x approaches 1 of f of x exists. Okay, we would actually say it's 1, right? We say it's 1. But f of 1 does not exist, right? It's just a hole there. So again, just having number 2, that property alone, just having the limit exist, not enough to say continuous, as evidenced there, right? So just saying the function is defined is not enough to say continuous. Just saying that the limit exists at that value is not enough. Okay? And then one final piece here, the limit of the function as x approaches c must be the exact same value as the function value at c. Okay? And so let me show you then again what that would look like if it didn't hold true. So in other words, the function can be defined, the limit can exist, but if the limit as x approaches c of the function is not the same as the function value at that c, still not continuous. Let me just show you a quick picture, and I'll just kind of reuse this one right here a little bit. Okay, so I'm going to say 1, 1. Okay. So there the limit exists. Okay. And the function has a value at 1. So the limit as x approaches 1. So the limit as x approaches 1 of f of x equals 1, but f of 1 is 2. So the limit as x approaches 1 of f of x does not equal f of 1. Okay? It is only when all three of these things are simultaneously present that we can then say the function is continuous. So the function must be defined, the limit must exist at that point, and finally the limit and the function must be the same thing. If you are asked to check for continuity, you must show that you checked all three of these things. Okay? This is one of the major concepts that you will need to have down, all right, in preparation, for the AP test and also for, our tests as well. Okay? You need to have 1, 2, 3 shown in order to prove continuity. Okay? Showing only 2 of these things or just 1 of these things will not be sufficient, and you won't get full credit on an explanation. Okay? So just keep that in mind. You need 1, 2, 3. They're all there and important. All right. So questions on any of that? So this is one of the major definitions you need to know. Okay? Function is continuous at C if and only if this, this, and this. Okay? So that's the idea. All right. A function is continuous on an open interval, a, b. Okay? Again, open because we're not including the endpoints there. If it is continuous at each point in the interval. So, right, we were just talking about continuity at a point. Whoa, that'd be a lot of points to go through. But we can say a function is continuous on an open interval if it's continuous at each point in the interval. Now, obviously, we're not going to check every point there, but anyway, if a function f is defined on I, this is again talking about an interval here, except possibly at C, and f is not continuous at C, then f has a discontinuity at C. Okay? And there are 2 categories of discontinuity. So we talked about continuity, right? Now, if something fails, and if a point fails in an interval to follow all 3 of these things, we say we have a discontinuity there, and there's 2 kinds. And I think, again, this should be familiar to you from pre-cal, I believe. We talked about these, right? So removable discontinuity, okay, the typical one. If I just draw a function here, something like that. Okay. It looks like this, right? It's a hole. Okay, the typical kind of like removable discontinuity that we think about is a hole. Okay? The idea here, right, we call this removable because we can kind of like, fill in the hole. All right? We could fill that single value in and kind of fix the function so it's continuous. Wow, that looks like awful. Let me rewrite that. Fill in the hole. Okay, is the idea there. Fill in that hole. Okay. So f, and the idea here is that f can be made continuous by approximately defining or redefining f of c, right? So again, this would be like c and then f of c right there. Okay, so if we redefine what f of c would be, we could fix it. We can fill it in. Removing that discontinuity, right? And that tends to show up, the way we tend to see it show up, right, is when we have like a polynomial over a polynomial and like we can factor and cancel, right? Factoring and canceling, that indicates that the cancellation part indicates there's a hole at that point where we're canceling stuff. Okay, non-removable discontinuities, these are essentially, it's kind of like, well, you just really can't fix these so easily, okay, as just filling in a missing piece or a hole, right? And again, I'll use our little a step function here or something like that. Okay. Or we can also see sometimes another example of a non-removable discontinuity would be like a vertical asymptote. Okay, something like that as well. You know, two different pictures there. Okay. Here, changing f of c, okay, again, c in this case, we'll call c the 0. Okay, changing f of c doesn't fix our discontinuity. Okay, we can't just make f suddenly continuous by defining f of c to be different or something like that. It's, you know, they're not going to quite work that way because of that jump. Okay, so different types of discontinuities. Questions on any of that? Ready to move on there? Okay. Next page. All right, so we're going to run into some examples here. All right, example 1. For each, sketch a graph, give the domain, and discuss the continuity. If it's ever discontinuous, tell, okay, whether it is, or, you know, describe it as being either removable or non-removable using the definition of continuity. Okay, using the definition of continuity. All right, so looking at 1 over x, right, this is one of our parent functions, so we should have a, you know, an idea about what this is going to look like, right? We have that vertical asymptote on the y-axis, and we also have a horizontal asymptote on the x-axis, so if you want to draw that in, you can. Okay, and again, we're just going to sketch it here, so I'm just going to sketch in the one piece of 1 over x, and I'll sketch in the other piece of 1 over x, like so. Okay, just like that. So, do we have a discontinuity here? Yes! For what x value? At 0, right? And we can see that in the function too, right? We're dividing by 0, makes the function undefined. Okay, so we have a discontinuity at x equals 0. So that means, what would our domain be?
Negative infinity union, or 0 union, 0 infinity.
Okay, yeah, negative infinity to 0, union, 0 to infinity. Very good. So there's our domain. Okay. And so what kind of discontinuity is this? Non-removable. So I'm going to add that in front here, and hopefully I left myself enough space. Non-removable discontinuity at x equals 0. Again, there's that asymptote idea. Okay. So why is it a discontinuity? What properties of continuity fail here? Which of our 3, if we're saying it's discontinuous, that means at least one of these 3 properties has to fail. So which one of those 3, or which of those 3 fail there? So for example, go ahead, Sarah, you want to say it?
Oh, the limit doesn't exist.
The limit! Okay, so non-removable discontinuity because the limit as x approaches 0 of f of x does not exist. Is that the only reason that there's a discontinuity there? Certainly the limit does not exist. That's right. Does the function exist at 0? Lily? Were you going to say the other one?
I was going to say one that here isn't defined.
Yeah, so right, f of 0, right, f of 0. And f of 0 does not exist or is undefined. Okay, and I would even argue that because both the function and the limit are undefined or don't exist, we really can't say that they're equal either. So really, I would say all 3 of our properties fail here. Yeah.
We have a question on like this on the test. Do we have to give both reasons?
So no, because so the question was, you know, we've got all 3 properties there. Do we need to show more than one kind of like reason that it's not continuous? And the answer is no, right? Once you've got one, can't be continuous. So I'm just showing here for, I guess, completion's sake, so you all can see. Any one of those would be fine to argue, though, there. Okay? All right, so now let's do this, but I'd like you guys to go ahead and graph this. Okay? We need to still be able to graph these piecewise functions. Go ahead, take like a minute or two, sketch the graph of this piecewise function. Let me see here. Yeah. So I'm going to put some tick marks on here. So go ahead and graph this. Again, this is very important that we're able to graph these piecewise functions. This is a pretty, lots of pieces to this piecewise function. So make sure you can do it. First, I'm going to try and do it as well here. Minus 2 extra, so it'll be down to, like down to, right, down to. Piecewise functions are super useful for evaluating functions and limits and things like that. Okay, so you want to make sure that you're comfortable with being able to graph them. Okay, you don't have a graphing calculator tomorrow, so you can do it yourself too. Okay. Let's take a look here. All right, here's what I came up with there. Okay. So leftmost piece here, right? This piece right here was the x plus 1 for x less than or equal to 0. So I started at 0, right? So it's on the y coordinate 1. It's filled in, and then just down one, right one, down one, right one, or sorry, down one, left one, down one, left one to put the slope there. Okay, and then for this next piece, start at 0, square it, plus 1. So we're starting at the 1 there, so they're joined up. You don't need to do, you see, I don't know if like you guys can tell, but I did like an open circle around the filled in dot. You don't need to do that. You can just join them up, you know. But it's helpful to you to just like have that point there. That's fine, okay? But it's not necessary. Anyway, then I did 1. 1 squared is 1, plus 1 is 2, so 1, 2. And then 2 squared is 4, plus 1 is 5, so 2, 5, but open circle because it's not filled in. At the x value of 2, we have a y value of 3, so 2, 3, just a point. Oh, it's lonesome there, all by its lonesome. Okay. And then finally we start with x value 2, plug it in here. 2 times 2 is 4, 9 minus 4 is 5. So again, we're back at the 2, 5, but it's an open circle. And then do 3, and then 4, open circle there, and then finally for any value of 4 and greater, well actually not 4 and greater, for any value greater than 4 will be a y value of -1. So there's what our piecewise function should look like. Okay. So when it comes to evaluating continuity of piecewise functions, all right, we have like two kind of major places we want to look. Okay, major place number one, you want to look at all of your actual parts and determine if any of the parts are ever discontinuous. So for example, x plus 1, we should remember, okay, x plus 1, no matter how, no matter what interval I graph of that, x plus 1 is always continuous. It's just a line. So lines are just continuous, right? They're nice and smooth. There's no jumps, holes, or gaps or anything like that. X squared plus 1, no matter how I graph that, it's going to be a parabola that's shifted up 1. No jumps, holes, or gaps there, no problem. 3, no discontinuities on its own. 9 minus 2x, it's a line again, right? So no discontinuities there. And -1, also never discontinuous. So major thing you want to check for piecewise functions, number 1, is just in the individual pieces themselves to make sure there's no discontinuities. But everything's continuous here. Major place you want to check number 2, I mean, if you look at this, right, I just went through all these pieces and I was like, they're all continuous. But if you look at this, this is not continuous, right? And so we also want to check where you are switching between pieces. So where we join up. So at 0, you want to check the continuity. At 2, you want to check the continuity. And at 4, you want to check the continuity. Any location where you're switching from one function to another, you want to check the continuity there. Okay? Just by looking at this, how many discontinuities, or how many x values, I'll say, how many x values do we have discontinuities? 2, right. The x value of 2 and the x value of 4, right? At 2 and 4, we have discontinuities. We have a potential discontinuity at 0, because we're switching from one function to another, but at 0, it joins up, and so we're okay. Okay, that one actually turns out to be okay. So let's check these. Let's just check x equals 0. Okay. Let's do our 3, parts to it. So step 1, we have to determine if the limit as x approaches 0 of f of x. Am I doing this? Oh, no. Step 1, we did f of 0 first. My bad. It doesn't really matter which order you do them in, but I'll keep to the same order as what I listed. So sorry. We'll do f of 0 first. Okay. What is f of 0? 1 in this piecewise function. Good. Okay. What is the limit as x approaches 0 of, oops, I'm using f, I should be using h. Okay, anyway. Okay, what is the limit as x approaches 0 of h of x? It's also 1, right? You can see it visually here, right? You can see it visually. Also, we can check either side here. We can check either side, right? From the left side, we're going to be using this x plus 1. We can do a direct substitution of 0. 0 plus 1 is 1, so that's good. From the right side, we're going to approach 0 using x squared plus 1. Again, we can try direct substitution there to evaluate it. 0 squared plus 1 is also 1, and so it's 1. And then finally, step 3, h of 0 equals 1, which is equal to the limit as x approaches 0 of h of x. And so there we have our 3 pieces. Check, check, check. We can now show that the function h is continuous at x equals 0. Okay. This would be a sufficient explanation. So it doesn't always have to be like sentences, right? You don't have to like write out words. You can just use, these are like mathematical sentences almost, right? You're using just symbols and stuff to help you explain it, as long as they're appropriate use of the mathematical symbols. All right, now let's check x equals 2. Right, another possible discontinuity there. All right, so step 1 is h of 2. What is h of 2? 3. Okay, good. What is the limit as x approaches 2 of h of x? 5, right? As we approach from the left and from the right, we're approaching the y value of 5 there, so it's 5. So check, check. These both exist. That's great. Okay. Step 3, h of 2 equals 3, but that's not equal to 5, which is the limit as x approaches 2 of h of x. And so we fail. Okay, we fail our test for continuity. Okay, H is discontinuous. And just for our purposes here, we'll say the kind of discontinuity, non-removable, because it did ask in our directions. Or sorry, removable. This one's removable, my bad. This one's removable. Okay, this one is removable, right? Because it's just a single point. We could fill in there to make it work. So it's a removable discontinuity. H is discontinuous because h of 2 does not equal the limit as x approaches 2 of h of x. Okay, bless you. All right, last one here. Okay, last one. All right, we're checking x equals 4. Bless you. Yes, question to me.
So if this was like one of the questions on the test and they asked you to define how it's discontinuous, would you have to go through all of the possible points or just one?
No, you can jump. You can, like, as soon as you get to one. And again, I was just going in order just because that was what I showed you the order. But no, if you send me, if you can see right away which one's going to fail, just go straight to that one. And that goes for anyone, right? Go straight to that one. You don't have to show, the 2 work, but 1 doesn't, right? As soon as you get one that doesn't, then we're good to go. All right. And luckily, again, going in order, we're our very first one here. What is h of 4? Does not exist. Okay. And so we're done. We don't even need to worry about step 2 and step 3 to check, right? We don't need to worry about those. And I shouldn't say they're even steps. They're not steps because you don't really have to do them in order. It's really just any of the properties. So again, our statement then, okay, H is discontinuous. And what type of discontinuity would this one be? Non-removable, right? There's that jump there. Okay, H is discontinuous at x equals 4, and I should have put that here, at x equals 2, because h of 4 does not exist. And I know I use D and E sometimes, but please be careful with that. Again, on the AP test, they don't like you to use abbreviations unless they're like, I guess already understood mathematically. So yeah.
If you know that it's going to be a certain one of the 3 that would make it discontinuous, can you just jump to
Yes, exactly. Yes, do that. And again, I'm just doing it here just kind of because I feel like I want to give you guys the practice of being able to see, hey, sometimes things do work, but then one of them fails. But of course, you all are pretty good, I think, visually at inspecting and seeing, wait a minute, these are going to fail. And so sometimes, maybe you can tell which one it's going to be, but maybe you won't be able to tell. And so you can just go through it until one of them fails too. Okay? All right, let's flip it over here. Okay? And I would like you to actually try this one here on your own. Okay? So this is for you to go through here and try. All right? So go ahead and try and answer these questions. All right? And there's some blanks for you to fill in, and I'll try and come around and help. But give this one a try here. Give this one a try. And you want to use your graphing calculators for number 2. Okay, you can just use your graphing calculators to do that. And number 6 as well, at the very bottom there. You're going to use kind of like your results to help with that. Bless you. Don't forget to give reasons for those very last two, A and B, right? Okay. Don't get 6A and 6B. Okay. Justify your answer means to give reasons, right? If you think it's going to be discontinuous, then you need to show that it is discontinuous. If you think it's going to be continuous, you need to show that it meets all 3 criteria. All 3 criteria. Any questions? Which one? First one? So, the way you have it typed in here, it's going to, I'm glad you grouped that, but you also want to group your denominator, because this is only going to be divided by x, and you subtract on the x. Okay, so really that fraction bar is a grouping symbol for the numerator and the denominator. So always put parentheses on the numerator and denominator, and then see. Let's see. So then also, if this continuous there, justify why this. Which criteria fails if you're saying it's discontinuous there? Okay. I see what you're saying. Yeah, I think we want it, yes. Thank you for pointing that out, Carter. I'm going to write that. I'm going to include that in here. Mine. I forgot. I missed that part too. So I'm going to fix that. But right? You realize that. So what we know here is, well, if we're not, if x equals 1 is on the point, then it describes everything else. It means x not equal to, so you're saying like this x not equal to 6. Determine the continuity of those pieces. So that's just it. Use the result of above steps to determine if on piecewise functions are continuous everywhere. So since that's the case, since it's not what it should be, right? So what I see what you're saying here. So I think you want to evaluate at -2 first, because that's where piecewise function is not just like the individual pieces. So we do want to consider that. So I'm glad you thought about that. But also you want to consider at -2 as well. So what I recommend, you kind of have like 2 places you want to. Yeah. Okay. But you also want to consider the fact that yeah, cube is where -3 is. Yes. Yes. Again, -2. Is that what you were? Yes. Correct. Yes, remove discontinuity, and yes, the limit does not exist. Or sorry, the limit and the function exist, but they do not equal one another. So yeah, that's fine. Good job. All right, Ursha, coming at you. You get that one. This one I don't know. Yes. So, in a similar fashion to what we did right here, okay, here we actually like fixed it so the thing would be continuous. So now I want you to evaluate this piecewise function, right? Is there going to be any discontinuity for this individual piece? Yes, at 3, but because the way we define the piecewise function, at 3 the value is 4. So, the function exists at 3, clearly it's 4. Okay, we need to check with the limit, because the limit exists of this function at 3. In other words, we define the limit of this. If you want to, sure, you should do it by hand too. Right? You can do that, just factor and cancel, and then plug the driver substitution. And then finally, does the function value of 3 is equal to the limit of this plus? The x squared plus x minus 12.
Well, then,
You should check before you just say it does. You should check. You should check. Yeah. Yeah. You should check. You should check. Okay, question.
I don't even know what to do.
I know you plugged it in, and I see the graph.
Okay.
I don't know.
So just go through your criteria, right? You can see there's potentially a problem at -2, right? Because that's what we're jumping.
Yeah.
-2.
I get there.
Okay, so does the function exist at -2? What's the value of the function? -2. It does, right? Does the limit of the function exist as x approaches -2? Now you're talking about this one, right? So anybody that's not equal to x means we're approaching it. Now use this. Take the limit of this as x approaches that -2. So take the limit of this as x approaches -2 and see what value you get. If it exists, then that's checked. That's criteria 2. And then finally check, does the function value equal the limit as x approaches -2? Or do you meet all those criteria? Okay. Yes. But there's a hole at 3.
Pretty easy, dude.
No, because think about what's going to happen here. You can factor this. Yeah. Divide by the x minus 3, the factors will cancel. In this case, you'll be left with what's going to be linear. Except if there's a hole in that one, you can't see it. So we can show it.
Would it be a non-removable or a removable one? I figured it out this week.
But can't we do something with this kind of function? What's the strategy where you can see the square roots?
Oh, we did that.
Yes. Yes. Luke?
What is
Who cares that they are?
Yes. So what's the value of the function at 3? 4. Or just limit approaching as x approaches 3. 3 plus 4 is 7. So you would say distance minus 8 because, and then you say f of 4 is not the same as the limit of x approaches 4.
And not here. At home.
Yep.
I feel like he doesn't go home.
Okay. I'll give you like 2 more minutes because I really want everyone to give these all a good shot. All right, so about 2 more minutes here.
We have to justify it as discontinuous, like we have to explain why it is discontinuous.
Yep, either answer you should be able to justify. I'll keep walking around here.
I feel like we just go home and where in reality he just crawls behind the bleachers and sneaks behind the trap.
Also, how would I write this up?
So the way you can write this is similar to how we see these right here. So for just the 1 forward x is 1, you got 2, so just say f.
You bring up the
Right, you can also use our analysis or analytical method. So let's again check for continuity, right? Does the function exist?
I know some people that
Let's do it at the negative. So does the function exist here too? What's the limit of our function? So this is what we're going to be using. Well,
I got a lecture
how do you
over
know
the phone.
you can take like a class,
I'm gonna go back
or you can evaluate this using our rationalization. You can rationalize this, and then you simplify and cancel, and then do a direct substitution negative 2 to see if you get 0.5. But again, if this were not a calculator, which it most likely would be. Okay, folks. Let's go through this here. Here we go. Okay, so number 1. We're going old school here. What is the domain of f? For our first, like our example here, what's the domain of f? Negative infinity to 1, union 1 to infinity. Is f continuous everywhere? No, right? It can't be. If we're excluding something from the domain, that means it's a discontinuity, right? Typically there. So there we go. Negative infinity 1, union 1 to infinity. F is not continuous everywhere. Okay, I didn't say to explain that at all, so we can just go from there. All right, investigate the graph of f of x using the table and graph around x equals 1. Okay, to see that f of x has a removable discontinuity at x equals 1. Good. All right, next we're asked to compute the limit as x approaches 1. X approaches 1. Okay, of f of x. And what is the limit as x approaches 1? 2. Okay, there's your work. Factor and cancel. Okay, next. How should f of x be defined at x equals 1 to remove this discontinuity? In other words, f of 1, we want it to equal what? 2, right? We want it to be 2, and so we'll make it equal to 2. Okay, we want f of 1 to be 2. So that way it would work. All right, so then to fix this function right here, which is discontinuous, this function is discontinuous, we'll fix it and make a piecewise function, okay, like so, where everywhere but x equals 1 will be the original function, but then at 1 we will fix it and make it 2, filling in that hole, okay, getting rid of removing the removable discontinuity, right? Okay, now, use these results from the above answers to determine if the following piecewise functions are continuous everywhere. Justify your answer. So, let's see here. I'm gonna need 2 sheets of paper because there's 2 problems here to block off. So, well, I guess I'm gonna kind of see it here. So there's our first function. Okay. Remember, for piecewise functions, we want to check the individual functions first for their continuity, right? But we also then want to check where we switch. And so you see we're switching at 3 here. Okay. So what is the value of the function at 3? What is f of 3? 4, right? Okay, some timid 4s, so that's right. 4, all right. What's the limit as x approaches 3 of 4? 7, right? How do we take the limit of this thing? Well, it's the same way we've been doing it, right? You just take, so if you want to take the limit of a piecewise function, since we're approaching 3, we're going to not use this. This is only true when x is exactly 3. Since we're approaching 3, we're going to use when we're approaching from values that are not 3. So we're going to use this, okay? Factor and cancel. Direct substitute. But Mr. Widmeyer, when I plug in a 3, isn't that saying that x is equal to 3? But this says x is not equal to 3, right? The difference is we are evaluating a limit. We're using the strategy of direct substitution, which allows us to plug in that limit. It's okay to do that here. Okay, we're using the strategy of direct substitution. We're direct substituting, but that is to mimic approaching the 3. Okay, that's all. So we're allowed to plug the 3 in for that reason, because we're evaluating a limit. Anyway, we get 7. So is the function continuous everywhere? No. Where is it discontinuous? 3. Not continuous at x equals 3 because the limit as x approaches 3 of f of x equals 7, which is not equal to 4, equal to f of 3, right? Or simply put, the limit as x approaches 3 of f of x does not equal f of 3. That's all you really need to say there, okay? That's all you really need to say. You don't need to give the specific values. You can just say that as long as you establish in your work elsewhere that it's, the values and things. Okay? All right, let's look at the next one. I guess I'll leave that up. Okay. All right, next one here, we did something similar, right? Okay, so again, we're changing from -2 to, we're changing at -2. So we want to see the limit, right? The value of the function at -2 is 0.5. That's easy enough to see. We then have to check the limit as x approaches -2 for criteria 2, right? And so we have to rationalize like we did, and we have plug in the -2, and we get 1/2. Aha! The function exists, 0.5. The limit exists, 0.5. And the function and the limit are the same value. So this function is continuous everywhere, right?
Yes.
I thought so too. But then thankfully Carter steered me clear of that mistake. And in fact, f of x is continuous. And there's other people that maybe did the same thing too, but Carter called me on it first there. Okay? And so the limit, the function exists at -2, the limit exists as x approaches -2, and the function value and the limit as x approaches -2 are the same value. So f of x is continuous at x equals -2. But f of x is discontinuous for x values less than -3 because the function does not exist for those x values. Why does the function not exist for x values less than -3? Because we're taking the square root of a negative. Okay? And so that's why I said in the beginning, right, that we want to keep an eye out for the individual pieces too. The individual pieces too. All right? This is no problem, but this, we're going to have problems for some x values when they're less than -3. Okay? So keep an eye out for that. Keep an eye out for that. Okay? Questions on anything before we move on? We still have a little bit more. Yeah, Sarah?
So basically it's just any even root going to be discontinuous?
For an interval, yeah.
Okay.
Yeah, for an interval, yeah. But you still then also want to show, like, so if we were discussing the continuity of that kind of situation, you want to, obviously show that you've looked at that, the square root of negatives and stuff like that. But you also want to consider the places where it jumps, or where, like, the pieces change and stuff like that, too. So you really got to consider both, okay, everything.
So, or just for like purposes, if there was another line that continued off of where x was less than -3.
If this was like an interval, for example, instead of just everywhere but -2. So if this was like for x values greater than -3 and then x equals -2, then yes, you could make it continuous or something. Or if you just limited it, it could be discontinuous still.
And if there was also a line that continued.
Sure. Yep, that'd be fine too. Yeah. Yep. Okay. All right, moving on. We have one more little piece here we got to cover, and that's that last page. Now we're going to talk officially now about one-sided limits. We've already kind of been using the idea when I talk about approaching from the left approaching from the right, okay? But now we're actually going to do that here, okay? So one-sided limits, we're now, when we think about this, we're not going to be approaching from both sides, just one side. So the limit from the right as x approaches c, okay, is from values that are greater than c. Greater than c. So you denote that here. You can see it barely. Okay, there's a little c with a plus sign in the exponent. That's from the right. That's from values greater than c. Okay? For then the limit from the left, it's from x, as x approaches c, it's from values that are less than c. Okay, and again, you'll see a little negative in the exponent. Please be careful with that, okay? Because some students, they see the negative sign out front, and they get it maybe mixed up if they're approaching from the left. So just be careful. The negative is in the exponent, right? The positive is in the exponent. So just be careful with that when you're evaluating. Okay? So how do we do these left-hand and right-hand limits? Well, so let's see some examples here. I've got some stuff right here. All right, so for this first one, right, we're approaching 3 from the left. Well, since this function is continuous, right? There's no jumps, holes, or gaps. Approaching 3 from the left is the same thing as approaching 3 from the right, is the same thing as just approaching 3 because it's continuous, right? There's no weird behaviors in it. We can just literally just do a direct substitution. It'll be 3 squared minus 3 times 3 plus 1. And so this is just equal to 1. Okay, just equal to 1. That's it. Okay? Now, this piecewise function got defined in a little bit of a funky way. But anyway, for letter B, the limit as x approaches 1 from the left. And you'll see that our piecewise function is defined with 2 pieces and it switches at 1. Which of these 2 pieces should we use if we're trying to approach 1 from the left? Why the top piece? Because yes, we're approaching x from the left, or sorry, 1 from the left, which is x values less than 1. Where is our function for x values less than 1? Right there, right there. And so we'll evaluate it just like we did here. We'll do a direct substitution. So it'll just be 1 squared minus 5, which will then be negative 4. Okay. And then letter C, same piecewise function. Same definitions for the x values here, but now we're approaching 1 from the right, so which piece should we use? The bottom piece. And so it'll be, again, we can now just use a direct substitution. So 2 times 1 plus 5 equals 7. Okay. Taken together, we approach 1 from the left, it's negative 4. We approach 1 from the right, it's 7. What can we say about the limit as x approaches 1? Does not exist. Okay, the limit as x approaches 1 of that piecewise function x squared minus 5 to x plus 5, okay, does not exist. The left-hand and right-hand limit disagree. Okay, the left-hand and right-hand limit disagree. Okay? All right, so as we then go on to this, here we go. We're talking about the existence of a limit. Let f be a function, and let c and l be real numbers. The limit of f of x as x approaches c is L if and only if. The limit as x approaches c from the left of f of x is L, and the limit as x approaches c from the right of f of x is L. Okay, so this is in easier terms to say, right? Okay, the limit as x approaches c from the left must approach that value L, and the limit as x approaches c from the right must approach L. So from the left and from the right, you have to be in agreement with what you're approaching there. Okay. I will skip example 4 for right now. I think you're going to see stuff like this. I mean, I think you can determine you're just going to approach from the left and from the right. But I want to talk about number 5 just so that way we have enough time to really discuss this well. Okay, so number 5, and this is like a classic kind of problem that shows up on AP tests or this kind of concept and stuff like that. I think you might even have a question in your homework and stuff about that. It's just kind of classic. I don't know. I just remember seeing this. It's like a typical kind of problem that you'll see. So determine the value of C that will make G continuous everywhere. Make G continuous everywhere. Okay, so let's take a look at our individual pieces here first. C is just going to be a constant. So 2x plus c, will that ever be discontinuous? The individual piece? No, it's a line, right? This is e to the x. We can plug whatever x value we want into e to the x. Here the square root, may have some trouble, right? What x values are going to give us trouble here? Anything less than -1, but do we have to worry about that? No, because according to our piecewise function, we're only going to be plugging in x values greater than or equal to 0. So the individual pieces, no problem, will be continuous for these particular intervals. So what's the only potential for a discontinuity here at what x value? 0, where we switch from the first one to the second one. So now we need to check our criteria. All right. First thing we want is, not f, we want g of 0. We want to know what that value is. Okay. How can we figure out g of 0? Which part of our piecewise function do we evaluate? The bottom one, because that's where x is equal to 0. So we'll say it's e to the 0 plus the square root of 0 plus 1. So e to the 0 is 1. 0 plus 1 is 1. Square root of 1 is 1. So we get 2. G of 0 is 2. So g of 0 exists. Check. Criteria 1. Next, we want to evaluate the limit as x approaches 0 of g of x. How do we evaluate that? Which part of our piecewise function are we going to be checking the limit of? Bottom and the top. We got to do both, right? Because if we're approaching 0, that means we have to check what approaches 0 from the, or what the function approaches as we approach 0 from the left and from the right. So we'll do a direct substitution here for both. So let's do the limit as x approaches 0 from the left. Okay, the limit as x approaches 0 from the left, that's this one. So it'll be 2 times 0 plus c, which is just going to be c. And then the limit as x approaches 0 from the right of g of x, it's going to be this piece, right? And so it's going to be, well, we know it's got to be 2, right? We just did that right here. We plugged in 0, so it's got to be 2. So the left-hand limit is c, the right-hand limit is 2. What must the value of c be to make g continuous everywhere? It's got to be 2, right? C has got to be 2. Okay, it's got to be 2. And there it is. We figured out what it has to be, right? Because now the limit and the function value will also be equivalent. G of 0 equals the limit as x approaches 0 of g of x. Okay, so check that one too. And so it's got to be c equals 2. Okay, that's how you do that. All right, just run through your normal criteria thing and then use the idea of continuity to help figure out that c has to be 2 to make it work. Okay, that's it. That's all. Okay. So again, these concepts, one-sided limits, right? Continuity will not be on tomorrow's test, but they could be helpful. Okay, they could be helpful. Homework is also on Google Classroom as well. Okay.
No, because then after 90 days, I won't have to hear it anymore.
What's that? Set. Yes. Other set requests for today, Morgan? Celia, got it. Chase, got it. Anybody else for set today? Set requests, quiz tomorrow.
I did it last year too. Semester 1 had
Make sure you can graph those piecewise functions, folks. Make sure you can graph those piecewise functions. Okay? Yes. Is it quiz difficult? I think I would probably get an A on it. For you, I mean, I think it would be more difficult in the sense that limits are a, more conceptual thing. So it could be, but I mean, again, it's what we did past today. So I mean, if you feel like you did pretty well on the homework and stuff, again, similar, yeah. What's that? Someday, yes.